I will come to the next stage. After secondary refining, what do you do with the liquid steel? You have to do the casting. So, whatever processes you have used for making a clean steel, that means you have controlled all these elements, undesirable elements. You have controlled dissolved oxygen, you have controlled sulfur, you have controlled nitrogen, you have controlled hydrogen, you have controlled carbon if it is a necessity, you have controlled phosphorus of course in primary steel making stage. Now, you do not want this good steel, which is a relatively clean steel after secondary refining, to get contaminated again during the next casting stage. So, all the steps which you have taken for secondary refining, for cleaning, should not go to waste. How do you do that? Because in casting, that means what you have to do, you have to prevent reoxidation and renitrogenation during transfer of liquid steel from ladle to tundish and to mold. I will just first discuss with you how the continuous casting takes place. You have done all the refinings in ladle. So, the liquid steel which is relatively clean is in ladle. So, this from ladle liquid steel now has to be poured to tundish, which is intermediate, is a buffer sort of container which maintains liquid steel during casting, and from this tundish it will be poured into the mold of the caster. So, first the ladle has to be fixed, then from ladle liquid steel comes down to the tundish, and from tundish it comes down to the mold for continuous feeding into the caster. So, this is the stages. Here this tundish, there is a close up of the tundish, it is shown in a larger size what happens in tundish. I will now one by one discuss how this ladle, tundish and mold, we have to be careful about everything, all the steps, so that whatever steps we have taken for cleaning the steel do not go to waste. The steps which we have taken to clean the steel should not be going to waste. That means, we have to be careful that whatever cleanliness level we have achieved, it should not increase. Cleanliness levels again should increase only, it should not decrease. That means, all the elements, particularly oxygen, nitrogen, which are there in air, which there is a possibility of pickup of oxygen, that means reoxidation, pickup of nitrogen from air, that means renitrogenation during transfer of liquid steel from ladle to the tundish, from tundish to the mold. So, we have to be very careful. How do we do that? That is what we are telling, we have to prevent reoxidation and renitrogenation during transfer of liquid steel from ladle to tundish and again from tundish to the mold. This is the first requirement. Then additionally, some more control measures have to be taken in tundish and mold for ensuring that the exogenous entrapment, new exogenous entrapments do not get into the steel, they are prevented. That means, from the ladle, from the tundish lining, or from the mold slag, there is a possibility of exogenous entrapment getting entrapped or entrained in liquid steel, which should not happen, which should be controlled, because we have taken all the important measures to clean the steel. We do not want the steel should again get dirty from the exogenous entrapments. The first our step is to prevent reoxidation and renitrogenation from air during transfer of liquid steel from ladle to tundish and then from tundish to mold, first step. Then the second step is to undertake some additional control measures, which I will be telling you one by one in ladle, in tundish and mold, to ensure that new exogenous entrapments from the ladle lining, tundish lining or tundish slag or the mold slag, they should not get entrapped or entrained in liquid steel. And if there is a possibility, we have to go for further improvement in oxide cleanliness, like the dissolved oxygen content. If it is possible, we should take measures to reduce it further, and we should get sufficient time for the oxide inclusions to float up. We should get sufficient time for the oxide inclusions alumina to get transformed to calcium aluminate of proper melting point, lower melting point, so that they become liquid at the liquid steel temperature, and it allows them for faster coming up to the liquid slag and get absorbed by the slag. So, in the process the oxide cleanliness increases. So, if you now look into this continuous casting steps, from ladle liquid steel is coming to the tun dish, which is a buffer, because continuously liquid steel has to be fed from tun dish to the mold. So, this is called buffer, the tun dish is called buffer, because after the ladle is emptied another ladle will come. So, the tun dish will maintain the liquid steel level, so that from here continuous feeding to the mold is possible. That is the beauty of continuous casting, unlike ingot casting. Ingot casting, one ladle emptied means the teaming is over. So, one heat, we call it one heat. One heat is one heat means one ladle. One ladle is emptied means the heat is teamed. One heat has been teamed in ingot molds. So, the teaming is over. But here ladle after ladle can continue. One ladle will be emptied, another ladle will come. Tun dish acts as the buffer. Continuous flow to the mold is possible. We can go to 10, 15, 20, even hundred of hits. So, one after another ladle will come, tun dish will be there. So, it is important to maintain cleanliness level in tun dish. Tun dish refractory is important. There should not be erosion. There should be sufficient amount of residence time for the liquid steel, for the inclusions to float up. These are the issues which I will be taking up one after another. So, first, as I was telling, from ladle liquid steel is coming down to the tun dish. So, there is a flow control, because liquid steel cannot drop on its own, the flow has to be controlled. How much of liquid steel flow velocity you want from ladle to tun dish, that is important. So, there is a flow control here at this stage, at the bottom of the so there may be a slide gate. So, there is a flow control device like slide gate. There may be a different device also for flow control. So, what is important here is, whenever liquid steel is coming down from ladle to tun dish, it is coming down through a refractory shroud. On top of that, we are pushing argon, we are doing argon shrouding. So, there is a refractory shroud, there is a argon flow on top of that. So, this helps, the refractory shroud as well as the argon shrouding, this helps in controlling reoxidation and renitrogenation, nitrogen pickup. So, it will control oxygen pickup, it will control nitrogen pickup from the air. So, first the refractory shroud as well as argon flow. How much argon will be flown? These issues I will be discussing. This will show to what extent argon has to be flown, to what extent oxygen reoxidation can be controlled, renitrogenation can be controlled. So, this is one. Another one is, again from tun dish to mold, there again has to be a flow control, either by slide gate or by other means. So, here again it is flowing, liquid steel is flowing from here to the mold through a refractory nozzle, which is called sub entry nozzle, because it is submerged in the liquid steel during casting. So, it is called sub entry nozzle. So, again there has to be argon flow in the sub entry nozzle. So, to control nitrogen pickup and oxygen pickup. So, these two are very important, argon injection here at the flow control level from ladle to tun dish, and again from tun dish to mold. This is first requirement. There is a ladle shroud as well as argon injection. Here there is a it's called sub-entry nozzle, some shroud, it is a refractory shroud, and as well as there is an argon injection. Now, let me first then come to the how much of this argon, how much of inert gas has to be flown, how do we decide? So, what are the measures in ladle to control entrapments? First, when the liquid still is there in the ladle, initially we have to put you have to put some sand in the slide gate before we are pouring liquid still from BOF in the priming stage. When you are pouring liquid still from BOF or electric arc furnace, first the ladle has to be closed. That means we are putting the slide gate, we are putting some sand to close the output of the ladle, the exit of the ladle. So, when we start teaming, that means when the ladle has to be opened, the slide gate, when it is opened, the sand, whatever sand was there in the slide gate at the nozzle, that will try to come down and fall in the tun dish. We do not allow it, because it is, what is that? This sand is basically means is some exogenous entrapment, it will cause exogenous entrapments, it will deteriorate the cleanliness level. So, first that has to be checked, it should not fall in the tun dish. We should try to just take it out. When it is just falling, we should not allow it to fall in the tun dish. Next is free opening of ladle. When you are controlling the slide gate, we are allowing the liquid steel to come out from ladle to tun dish. We call it free opening is possible when just when you are pulling out the slide gate, it should fall. That means liquid steel should come out, because we do not want it to be poked with oxygen, because when oxygen lancing is, if it is required, that means it will create reoxidation. When you are trying to open the ladle, it is not free opening, then we are trying to open the ladle with oxygen lancing, because steel has got stuck, steel has got solidified at the exit. So, we are using oxygen lancing, which is not desirable. What is desirable is free opening of ladle. The slide gate, when you open the slide gate, liquid steel should flow out, come out. So, it is called free opening of ladle. So, prevention of ingress of slide gate sand, control of that is first requirement when you are opening the slide gate. Next, the ladle should open free, that means the slide gate, when you are trying to open the slide gate, liquid should come out without oxygen lancing, without the necessity of oxygen lancing. If you do oxygen lancing, it does not open free, so that means we are creating reoxidation, which is undesirable, as I have told many times, which is undesirable. Now, we have, suppose we have controlled the sand, we have opened the ladle free, so the liquid steel is coming out from the ladle, as I have shown you, liquid steel is coming out from the ladle to the tun dish through this shroud. Now, we have to make some iron injection, we have to push some inert gas, that means iron. So, now how is it done? We can, there has been some experimentation for this. The argon shrouding is definitely useful compared to nitrogen shrouding. If you use nitrogen, what is going to happen? Say we are using 60 liter per minute of nitrogen. So, it has been found that there will be an increase of nitrogen pickup to the extent of about more than 20 ppm. If you reduce the nitrogen flow to 30 liters per minute, even with this there will be a 15 ppm of nitrogen ingress, nitrogen increase in liquid steel. Now, if you use, instead of nitrogen, if you use 30 liter per minute of argon, still some amount, a small amount of nitrogen is pickup is there, because 30 liter per minute of argon may not be adequate to control air ingress, and if air ingress is there, like oxygen, there will be some nitrogen pickup also. If you use 60 liter per minute of argon, this is a flow of argon. How much argon do we pass? It has been found out, there is an experimentation. So, all these are important to note. So, if you pass 60 liter per minute of argon through the shroud, even with this there is a small amount of nitrogen ingress, 5 ppm of nitrogen. Where from nitrogen is coming? From the air. That means some amount of air is still entering the system. So, if you use 100 liter per minute of argon, then there is no nitrogen pickup, and if there is no nitrogen pickup, there will be no oxygen pickup as well, because no air ingress is there, it is taking place. So, 100 liter per minute of argon, it has been found experimentally, is required, is desired to control oxygen and nitrogen pickup. So, this is very important. We must remember that when we are pushing argon for shrouding purpose to prevent oxygen and nitrogen pickup, how much argon do we push? Because argon is is expensive compared to nitrogen. So, how much do you push? If you push 30 liter per minute, it is not adequate. 10 ppm nitrogen still pickup will be there. If you put 60 liter per minute of argon, still 5 ppm. If you push 100 liter per minute of argon, if you are allowing 100 liter per minute of argon to flow, so there will be no pickup at all. So, we have to remember 100 liter per minute of argon is useful. So, we do not go to beyond this level, because argon is after all expensive. So, this is adequate. So, now when you are using the shroud, as I was just showing to you that this is the refractory shroud. This shroud has to be immersed in the tun dish. If it is just above the tun dish, then again there will be an open flow, so which we will call reoxidation and re-nitrogenation. So, this has to be immersed in liquid steel. To what extent you immerse? Again some experimentation can be done, but important is it has to be immersed in the liquid steel in tun dish. Similarly, from tun dish, when it is coming to the mold, it has to be immersed. How much will be immersed? I mean, lot of thermodynamics, lot of kinetics is there, lot of experimentation has been there, but what is important is it should be immersed. Liquid steel should not be allowed to flow through air, directly flow through air, to prevent oxygen and nitrogen pickup. So, as I was telling that this is the level of oxygen flow which is necessary to control oxygen and nitrogen pickup when liquid steel is coming down from ladle to tun dish. Again, deep immersion of shroud from ladle to tun dish, deep immersion is necessary. Then another important thing is, so when liquid steel is coming down from in the ladle, it is coming down to the tun dish. As I was discussing, say liquid steel, it is getting emptied, it is coming down to the tun dish. From tun dish again it will come down to the mold. So, tun dish, the ladle is getting emptied. So, on top of the liquid steel, what is there? There is a slag, because this slag was generated during the secondary defining processes. During the different secondary defining processes, we need slag, So, slag was there at the top of the liquid steel. So, what does slag contain? It contains oxides, it contains calcium oxide, some amount of MgO, it contains some amount of small amount of maybe Al2O3. So, these are the oxides, small amount of maybe iron oxide which is not desirable, maybe small amount, maybe manganese oxide though it is not desirable, some amount of SiO2 though it is not desirable. So, the slag contains only oxides. So, when the liquid steel is coming down, the slag is also coming down. Finally, when the liquid steel is, when the ladle is empty, that means liquid steel has totally come down. So, we should not allow the slag to come down after liquid steel and get into the tun dish, because slag is an exogenous constituent, is basically oxides. Liquid steel is liquid steel, it is steel. So, we do not want slag to get into the tundish, into this, entrained into the liquid steel. So, we have to stop the slag from getting into the tundish. So, what do we do that? How do you know when slag will come? So, there is a technique. There has to be a detection system to prevent carryover of slag. That means, at the bottom of the, at the exit, at the flow control, here there has to be a device which will give an indication that yes, slag is starting now. So, immediately the slide gate will be closed. If you close the slide gate earlier, then what happens? That means the total steel has not come out. That means the yield is coming down, you are wasting some liquid steel, it is a good liquid steel, it is a clean liquid steel, we have taken all the measures to clean the steel. So, we do not want too much of liquid steel to remain on the ladle, after all it is going to waste. So, we want that as much amount of liquid steel, whatever good steel we have produced should come into the tundish, but we do not want the slag to come into the tundish. So, we have to make a compromise. When do we stop the ladle? When do we control the flow of the liquid steel? So, this is what I have been telling, that there has to be a detection system to prevent carryover of slag. As I had mentioned you earlier, the primary steel which was produced in BOA for electric arc furnace, we had mentioned that the primary slag carryover is very undesirable. We have to control the slag, it should not come from BOA for EAF to the ladle during pouring. So, what do we do there? We use slag cutoff, we use some measure to control the slag from coming into the ladle. So, here also we use some other technique. So, it is a detection system, there also there is a detection system, here also there is a detection system to prevent carryover of slag. Now, when this is not there, you cannot prevent the carryover of slag. You do not know when the slag will come, when the liquid steel has been completely drained out and slag will get in. So, what do? You put some amount of liquid steel in ladle at changeover, because to be sure the slag does not come into the tundish, some amount of liquid steel you are wasting, because there is no, if there is no detection system, you have to waste some liquid steel at the time of emptying the ladle. So, some amount of liquid steel you keep, on top of that is slag. So, the slag cannot come inside the tundish. So, this way the yield of the liquid steel will slightly go down, but the quality will be ensured. So, no deterioration of quality, no exogenous entrapment of slag will be there. If the slag comes in, then this slag is an exogenous entrapment, it acts as an exogenous entrapment. We do not want ladle slag to come into the tundish. Like here also we do not want tundish slag to come into the mold. Tundish slag, this I will discuss later on, but right now I am discussing ladle. So, ladle, at the end of the emptying of the ladle, at the stage of that, we do not want slag to come to the tundish. This is very important. Now, I have discussed that ingress of slide gate sand when we are opening the ladle during tipping. This is important, this has to be prevented. The ladle should be free open, that means no oxygen lancing will be necessary, we have to be very careful about that. That is why the proper quantity of sand, proper characteristic of sand is very important, slide gate sand. This helps in free opening of ladle. So, free opening is a requirement, because if there is no free opening, then you have to use poking, you have to use oxygen lancing. In the process some amount of liquid steel get reoxidized, and this will contaminate some amount of liquid steel, which is again going to the tundish. So, reoxidation, renitrogenation will take place. So, next is some argon shrouding is necessary. Now, I have shown and discussed how much of ladle flow is necessary, about 100 liter per minute I have mentioned is necessary to control or to prevent oxygen and nitrogen pickup. Any amount of argon will not help, 30 liter per minute of argon, still there is some nitrogen and oxygen pickup, because some amount of air ingress will be there. So, if it is 100 liter per minute of argon, then air ingress is controlled and there will be no nil pickup of oxygen and nitrogen. Then what is important is deep immersion of shroud. This is very important. It helps in preventing liquid steel to be exposed to air, because it is coming through the shroud, and there is the argon cover also. So, if the shroud is immersed in this thing tundish, liquid steel in tundish, then there is no scope for deoxidation or nitrogenation, no scope for contact with air. And then I have told you, if there is a detection system to prevent carryover slag, that is ideal. We do not want the slag at the end of the emptying of ladle to come into the tundish. Slag is an exogenous entrapment, we do not want that, it will affect the cleanliness level, it will increase the oxygen cleanliness level, oxide cleanliness level, we do not want that. And if that detection system for slag carryover is not there, then there has to be adequate liquid steel in ladle at the end of the emptying the ladle, so that slag does not come into the tundish. So, this is very important. Now, I will discuss about another important issue. I have talked about the refractories. There is a refractory lining in ladle. What type of refractory do you use? That is very important. I have told you that it has to be a basic refractory, because during secondary refining, if it is a basic refractory, then it will react with SiO2 and can take care of. And if it is a acidic refractory, that means if some amount of SiO2 is present, then it will react with aluminum and cause aluminum in liquid steel and cause alumina formation, which is getting entrapped in liquid steel, which is undesirable. So, the type of refractory is very important, it has to be basic, that we know. Now, suppose it contains some SiO2, it contains some sodium oxide, it contains some potassium oxide, if it contains iron oxide in refractory, then what happens? I have told you it will react with aluminum in liquid steel. How does it react? We will see that. Now, again the carbon in refractory is also very important. Refractory should not have any carbon. If the carbon level of refractory is almost nil, it is very good, otherwise it will react. I will come to that, how carbon is deleterious from the point of carbon in refractory is deleterious from the point of view of cleanliness of steel. This refractory, suppose we have some amount of carbon, we have some SiO2 in the refractory. This SiO2 will react with carbon and SiO gas, carbon monoxide gas is generated. If you have sodium oxide in the refractory, this will react with carbon in the refractory, we will call sodium as gas and carbon monoxide as gas. If you have potassium oxide, it will react with carbon and will generate potassium as gas and carbon monoxide as gas. Now, what happens to this SiO as gas and carbon monoxide as gas? This SiO will now react with aluminum in liquid steel. I have mentioned many times that we have deoxidized the steel, good amount of deoxidation is very good amount of deoxidation is possible only when we do deoxidation or killing with aluminum. So, some amount of aluminum will also be there as elemental aluminum in liquid steel. So, this elemental aluminum in liquid steel will react with SiO which is forming in the refractory between SiO2 reaction from SiO2 and carbon, and this will generate alumina and silicon in liquid steel. Similarly, carbon monoxide will react with, how carbon monoxide is forming? It is forming from the carbon reacting with carbon in refractory, reacting with SiO2, carbon reacting with sodium oxide, carbon reacting with potassium oxide. So, if these constituents are present in refractory, SiO2, sodium oxide, K2O, similarly Fe2O3 again if it is present, some examples I am giving. The carbon in refractory will react with SiO2 refractory, with sodium oxide with refractory, with potassium oxide with refractory, and generate SiO and carbon monoxide. So, carbon monoxide generation is bad, SiO generation is bad because they will react with aluminum in steel and form alumina. So, the alumina will get formed, which again has to be removed from liquid steel. We do not want alumina in liquid steel. So, this has to be removed from liquid steel, another problem. Then silicon carbon also increases in liquid steel, which is again we do not want. So, reaction between steel and refractory, we have to keep in mind that the impurity content in refractory in the form of SiO2, sodium oxide, potassium oxide, iron oxide, carbon should be less. So, this is an indication. Now, I have shown here if the impurity increases, then there will be mode of clogging. What is clogging? Clogging basically means jamming from alumina. This alumina, I have discussed several times, all of you by this time know that they are solid at liquid steel temperature. So, if there are alumina particles in steel, even if there is some small amount of aluminum which is always present in liquid steel when we are killing with aluminum, if the steel comes in contact with air, alumina forms. Here the reaction between steel and refractory lining, again alumina is forming. This alumina, which is solid at liquid steel temperature, will clog the orifices, which will clog the outlet of the ladle, which will clog the outlet of the ladle, that means outlet of the refractory nozzle. If it is from the ladle to tundish or from tundish to mold, it can clog everywhere. Normally, if you go to the steel plant, if you are doing teaming with aluminum kiln steel, you will find that during teaming the nozzle is getting sort of choked. There is a ring formation of alumina when it comes into contact with air. So, this is because of alumina, which is solid. So, we do not want alumina to be present in liquid steel. So, alumina can be present if there is an reaction with oxygen, as I have told several times. Also, it can present if there are impurities like oxygen, SiO2, sodium oxide, potassium oxide, iron oxide, and carbon in refractory, which is reacting with liquid steel. So, refractory has to be quite clean. Refractory impurity level in refractory should be good, then only we can control the cleanliness of steel. So, this is very important. We want clean steel. So, you also want clean refractory. We want good quality steel, we also want good quality refractory to get clean steel. This issue is very important, because after all metallurgical vessels has refractory. Ladle, there is a refractory lining. So, this refractory should not have too much of impurity. Here you see, if the carbon free material you are using, the clogging level is almost negligible, and if you are using high level of impurity in the refractory, clogging level is increasing. If the clogging level increases, means we have to interrupt the process sometimes if this is very high. The exit of the the nozzle exit, gets choked if there is too much of clogging. That means basically it is choking off the exit, choking of the nozzle, refractory nozzle. So, this is creating, this will create problem during tubing. So, this is very important. We must try to remember this. Now, let me talk about, like as I have shown you earlier, that from ladle we are allowing the liquid steel to form in the tun dish. This is a bigger view, larger view of the tun dish, and from tun dish liquid steel is getting into the mold. So, one ladle, depending on what is the heat size, it may be 150 ton, it may be 200 ton, 250 ton, 300 ton. So, after this amount of liquid steel is poured in tun dish, the ladle is removed and another ladle will come. So, liquid steel is still there in the tun dish. So, tun dish life is very important. Tun dish is there for quite some time. Tun dish is there for several heats. Ladle maybe after one heat you are removing it, and we can inspect it if that ladle that refractory erosion is there or some problem is there with refractory, maybe we have to change it, do some patching. But the tun dish, there is several hits, several thousands of tons of liquid steel will get into the tun dish continuously. So, the tun dish refractory is very important. Now, how does it happen? What are the possibilities? What do you do in tun dish? First, let us see how does tun dish look like. The ladle, from ladle liquid steel is, this is the nozzle, refractory nozzle. From ladle liquid steel is coming down in the tun dish through this nozzle. I have mentioned nozzle must be immersed in liquid steel. It should not be at the top of the tun dish, so that there is no air ingress. It must be immersed in liquid steel. Then liquid steel flows, and then within the tun dish there is some residence time. This is very important. We should allow the liquid steel to remain in tun dish for some time, so that whatever inclusions are there, they should float up and get absorbed in the slag here. So, and then finally liquid steel comes down to the mold. Again there is a refractory nozzle, there is a stopper rod or maybe some slide gate mechanism. This is important. Here stopper rod is shown, there may be a slide gate as well at the exit of tun dish to control the flow of liquid steel. Now, what is happening here? Look at what is mentioned here. One is oxidation of aluminum by air and absorption of nitrogen. Whatever I was telling, that in the top of the tun dish there is a possibility of reoxidation and renitrogenation by if the liquid steel comes into contact with air. So, it must be covered, the liquid steel in tun dish must be covered with some slag. This is very, very important. There has to be a slag cover, both from insulation point of view, so that the temperature of the liquid steel does not come down very fast. Also, to prevent reoxidation, to prevent renitrogenation, there has to be a slag cover. Then what is happening, just see, when liquid steel is flowing, after it comes down, is flowing, that 2 is basically at the interface of the slag. So, oxidation of aluminum by FeO, MnO, SiO2 from slag. So, slag again is very important. As I have told you, for ladle slag, here also slag should not have constituents like iron oxide, manganese oxide, SiO2, otherwise the aluminum in liquid steel will get oxidized and alumina will form. So, this is important. The slag constituent, what will be the slag, that is very important. Next, what is happening here? Liquid steel is there, there is a continuous flow. So, at this point, that means the refractories should not get eroded here, should not react with the liquid steel. So, at this point, here also refractory, there is a possibility of refractory erosion, there is a possibility of reaction of liquid steel with refractory, those should be prevented. Otherwise again the cleanliness level will go down, exogenous entrapment will come up, steel will become dirty. Then there is a possibility of deoxidation reaction and inclusion removal in steel. That means if there is some soluble oxygen in the liquid steel, there is a aluminum in liquid steel. So, there is a possibility of some deoxidation, aluminum reacting with oxygen forming alumina. So, there is a possibility of deoxidation reaction, and whatever deoxidant, that means alumina they are forming, we should allow them sufficient time to float up and get absorbed in the slag. So, slag is very important here. What type of slag you use is very important. Normally 2 level of slag is used. The top level of slag is basically insulating type. You should not allow the temperature to come down, temperature of liquid steel, it should be insulating type. So, normally it is rice husk which has been used, it is a good insulator, but the carbon in rice husk is very important. It should not be, the carbon in rice husk should be low, otherwise there will be carbon pickup, but that is a top level of the slag. Below that there has to be a basic slag. Why basic slag? Because again I am repeating, this basic slag should not contain iron oxide, MnO and SiO2, otherwise this slag will react with dissolved aluminum in liquid steel and generate alumina, which there is a possibility of getting or contaminating the steel. So, there is a 2-stage slag we call it. The top one is insulating type, rice husk type, and below that there is a basic slag which will be useful for absorbing the alumina inclusions which will float up. This is very important. So, how do you increase the residence time of liquid steel in tundish? You see the flow, you are not allowing direct flow, you are allowing the liquid steel to flow this way. That means you are increasing the residence time of liquid steel in tundish, so that flotation of the inclusions is facilitated, inclusions get sufficient time to float up and get absorbed by the basic slag. So, how do you do it? You can use some dam, it is called dam, you can use some other constituents, flow control devices which will allow the steel to flow in a circuitous way, which will not allow direct flow from here to the exit of the tundish. So, it is a circuitous flow, that means you are increasing the residence time of liquid steel in tundish. Here look at what is there, it is a pad sort of thing which tries to protect the bottom of the tundish, because liquid steel will come down, and I have told you that it is immersed slightly lower below the top level, below the slag level, to protect the liquid steel. So, whatever liquid steel is coming out, it might impact the bottom of the refractory lining, the bottom refractory lining of the tundish. To protect it, there is a pad, there is a special refractory lining, special refractory component device which is called a charging pad at the top of the lining material. So, it prevents selective erosion of the lining at this point, because the liquid steel will impinge here, the incoming liquid steel will impinge here. So, it has to be protected, this area is protected. So, it is called a charging pad. So, what I have told you is the design of tundish is very important. It will allow, it should allow liquid steel to flow not directly, but in a circuitous way, so that the residence time is more, the inclusions can float up, this is very important. For that, dams, weirs, things like that, flow control devices are used at particular locations. So, that is design of in tundish to enhance the flow control, to increase the residence time. There should not be too much of dead volume. The liquid steel whatever is coming should not stay at a particular location. There should be a continuous flow, but the residence time should be more. So, this is very important. The dead volume should not be high. This is very important. So, this charging pad has to be there to protect this particular location where there is a possibility of impingement of liquid steel, coming liquid steel with the bottom at this location. So, these are important issues. Thank you very much.